Good morning. Today I will talk about axial load, normal stress and strain. So our topic today is axial load, normal stress and strain. Assume we have one bar or rod I attached to the fixed support, and assume it is in two-dimensional space, it is in plane structure, or even if it is 3D, no big difference for this case. If I apply external load like P here, fixed support from static, we know for in plane structure, in fixed support, we have three reactions. We have axial reaction, we have shear reaction, and we have bending moment. Here, because our external load only it is axial load, so this shear force reaction will be equal to 0, bending moment reaction is equal to 0, and we will have only axial reaction. So I can remove these. And we apply this external load in the centroid of the cross-sectional area. For example, if the length for this, it is L naught, and initial cross-sectional area for this bar, it is A naught. And the cross-sectional area shape, assume it is square shape. We apply this load exactly in the center. The cross-sectional area, it is A naught, and we apply force here, P, exactly in the center. If I pull this, if I apply tension, here reaction will be again Py, because summation of forces in horizontal direction should be equal to 0. If this is, for example, point A, and I assume this reaction, it is AX, what I have, summation of force in horizontal direction is equal to 0, so external load P minus AX should be equal to 0. From here, AX will be equal to P. So this bar will not move in horizontal direction because this P and the reaction P, they will cancel each other. Now if I cut this bar in one location away from the external load, a little bit far, for example here, the reason I'm telling far from the applied load point, later on I will explain why. But for now, assume we cut it, cut this rod perpendicular to this bar. What will happen? If I look at to the equilibrium of this piece, I have this part of the bar, external load is P. Now, if we look at to this free body diagram, in order to have this in equilibrium, I need axial force N here to keep this segment in equilibrium. That axial force N should be equal to the P, and they should cancel each other. This axial load I can show in another way. If I divide that axial load to the initial cross-sectional area, A naught, I can show with sigma, lowercase sigma. Internal axial load divided by initial cross-sectional area. We call this normal stress. Pay attention. The section cut is perpendicular to this bar, and the cross-sectional area it is A naught. And I divide internal axial force N to, I divide internal axial load N to the cross-sectional area A naught. We call it this normal stress. If I apply this load, if I pull this bar, what will happen? We will have elongation. If I show this elongation or deformation with delta, and I divide that delta by initial length L naught, what what I have, I can show with epsilon, we call this strain. So, what is the stress, normal stress? We should cut perpendicular to the bar. The normal stress component, so, will be perpendicular to the cross-sectional area. And if we divide internal force by initial cross-sectional area, what we will get, we call it normal stress, and we will show it with sigma. Strain is epsilon. What is the epsilon? Deformation divided by initial length, we call it strain. You should pay attention. Always once we are dividing, we should divide force by initial cross-sectional area and deformation by initial length. There is a special reason for that. Later on I will talk about that. These stress and strain, we call it engineering stress and strain. Later on we will see we have different stress and strain which we will use in science. But in engineering, stress always is force divided by initial cross-sectional area, deformation divided by initial length. In engineering, this is stress and strain we will use. But in the physics, in science, a little bit there is difference. Later on, I will talk about that. So, for now, we know what is the normal stress, what is the strain. So I show the distribution of the normal stress. If I cut this, and again I show that segment, here, this component, I show with sigma, normal stress, is equal to P divided by A naught, initial cross-sectional area, and we call it normal stress. Normal stress is always perpendicular to cross-sectional area. And strain is entire deformation delta divided by initial length. We call it strain. So this is stress, this is strain. Stress always we will show normal stress with lowercase sigma, and strain we will show with epsilon. Pay attention. If we cut close to the applied load location, a little bit closer, the stress distribution will not be uniform. In that case, the stress distribution will be something like this, non-uniform. And this sigma, in that case, will represent the average normal stress. But if we cut away from the effect point of the external load, far from that, the distribution becomes almost roughly uniform. So normal stress, external load divided by initial cross-sectional area, strain is deformation divided by initial length. Now let's look at the unit for stress and strain. What is the unit for stress and strain? Let's again look at the formula. Sigma is equal to P over A naught. What is the unit for P? In SI system, for example, unit for P, it is Newton. For A, it is meter squared. So the unit for stress will be Newton per meter squared. Newton per meter squared, we show with Pascal. Or in British system or US customary system, we know the force unit is pound. And the unit for cross-sectional area, for example, it is inch squared. So the unit will be PSI. But how about the strain unit? The strain unit, what is the definition for strain? Elongation or deformation divided by initial length. If the elongation or deformation unit, for example, is meter, and the initial length unit is meter, or even in British system, if it is feet, the initial length unit is feet, or even if it is inch, the initial length unit is inch. So meter will cancel meter, feet will cancel feet, inch will cancel inch. So epsilon strain is unitless. There is no unit for strain. So for strain there is no unit, it is unitless. For stress unit, usually it is Pascal, which means Newton per meter squared, or it is PSI, pound per inch squared. These are units. Let's come back to stress definition again. See what we have here. Stress, as I mentioned, it is force divided by initial cross-sectional area, and strain is deformation divided by initial length. This definition, force divided by area, we know that from physics. In physics, if you remember, we called force divided by cross-sectional area, we call it pressure. So in physics, we call it pressure. In engineering, we call it stress. There is similarity and difference between pressure and stress. Usually, once we are talking about fluid, for example, like gas or like liquid, there we will report as a pressure. We will tell, for example, gas pressure, liquid pressure. So pressure we will use usually with fluid, gas or liquid. But in the solid form material, if our body state, it is in solid form, we call it as a stress. So that is one difference. Another thing, stress can be normal stress which perpendicular to cross-sectional area. If you remember, in this bar, I cut it perpendicular to this bar, and this stress was perpendicular to that, and we call it normal stress. Later on, you will see if our external load or internal load, it is tangent to the surface, F, we can divide force again by this area, which is force tangent to that area, A0, and we will show another stress, we will show with tau, we call it shear stress. So stress can be perpendicular to the cross-sectional area or can be tangent to the surface, but pressure always is perpendicular to cross-sectional area. Another difference about what type of quantity they are. For example, you know we have scalar quantity. What is the meaning of scalar quantity? For example, temperature is scalar quantity. We can report temperature using magnitude, or speed is scalar quantity. But we have vector quantity. For vector quantity, in order to report vector quantity, we need magnitude and direction. For example, velocity, or for example, force. Force is good example. For vector quantity, we need magnitude of the force and we need the direction of the force. So, pressure is scalar quantity. Later on, I will talk about that. I will explain more. But stress is not scalar quantity. It is another quantity. We call it tensor. Tensor, later on I will explain what is tensor. But for now, you should know different type of tensor we have. We have a rank 0 tensor. Rank 0 tensor means is a scalar. So, rank 0 tensor, we call it scalar. We have a rank 1 tensor. Rank 1 tensor is a vector. We have a rank 2 tensor. Rank 2 tensor, for example, we show, as an example, stress is rank 2 tensor, and we should represent in the matrix form. Later on, I will talk about that. I will show the matrix for stress, and we call it a stress tensor. So for now, you should know the pressure is scalar or a rank 0 tensor, but stress, even it is not vector, 1 degree is higher, it is rank 2 tensor. So, or they call it second rank tensor. Later on we will talk what is the tensor, what is vector, scalar, why we call it scalar as a rank 0 tensor, or vector rank 1, or why we call it stress rank 2 tensor. Later on I will explain all this, but for now you know what is difference. Let's refresh your memory about one concept. I'm sure all of you hear about that, you learn it in the physics, but let's again refresh your memory. Assume we have one spring. Assume we have one spring, linear spring, something like this. This spring length, for example, it is L0. I apply force here. If I apply force here, what will happen? If I pull this spring, I will have elongation or deformation in this spring. So that deformation or elongation I show with delta. Let's do one simple experiment. Assume we have a spring. I apply force, tension force, F. In the first step, force is 0. I apply 0 force, nothing. There is no deformation. Deformation is 0. Then I increase the force a little bit to the F1. Deformation will increase to the delta 1. Then a little bit I increase the force to the F2. Deformation will increase to delta 2, and so on. If I show these values in one coordinate, and I call the horizontal axis delta and vertical axis F, and I show these each one as one point, I will have several points. If I attach these points together, I will end up with one inclined line. Inclined line. Tangent of this line, tangent of this angle, is equal to force divided by delta. We call that K. We represent that with constant K. We call it stiffness of spring. So stiffness of spring, K, is equal to tangent of that angle, which is equal force divided by deformation. From here I can write force is equal to stiffness of spring times deformation. This is very important formula. You know from physics, we call it Hooke's law. Hooke's law. Robert Hooke in 17th century, he came up with this formula, and for that reason they call it Hooke's law. Definitely you heard about this Hooke's law. Hooke's law means in one linear spring, the force and deformation, they are proportional, and the proportionality is equal to stiffness of spring. We show with K. Here, if the force unit, for example in SI system, it is Newton, and the deformation unit, for example, it is meter, the stiffness unit will be Newton per meter, or in British system we can write with pound per feet or pound per inch, and so on. Now we can apply this concept to the material. How we will apply it? First of all, you pay attention. Here if we apply force to the spring, you can do simple experiment with one spring inside of your pen or something like that. If you apply force and then you remove the force, what will happen? The spring will come back to initial shape or deformation will vanish. But until certain amount of the force, we have that behavior. If we apply bigger force, what will happen? If we apply very big force, you will see after removing that force, a little bit deformation will return to the initial shape and the body will get a little bit initial shape, but we will have permanent deformation. For example, if in one spring, if I apply first small force F, I will have deformation delta. If I remove F, delta will come back to the 0 point and spring will regain the initial shape. But if force exceed from certain amount of the force exceed from the certain value, in that case, if I remove the F, a little bit it will come back to the initial shape, but we will have permanent deformation. So, deformation will be divided into two parts. One part, it is elastic deformation. That part, it comes back to the initial shape, and we will have permanent deformation. That we call it plastic deformation. And even in some material, the relationship between force and deformation, it is nonlinear. In this kind of material, maybe the behavior is elastic, means you apply the load, you have deformation, you remove the load, deformation will vanish, you don't have permanent deformation. It is elastic still, but it is not linear elastic. The deformation and force, they are not proportional. This kind of material, we call it nonlinear elastic. Pay attention in this course. All engineering courses you will have in undergraduate level, strength of material, mechanics of material, or mechanics of deformable body. All material, we assume they are linear elastic. Linear means the force and deformation, they are proportional. Elastic means if you remove load, deformation will vanish and it will regain the initial shape. So, our topic in this course, all formulation we will have in different chapters. All of them, it is valid, it is right in linear elastic material. Fortunately, most civil engineering and mechanical engineering material, in the small deformation limit, they behave like linear elastic. For example, steel, for example, copper, brass, or all other material, they behave linear elastic under small deformation effect. For example, if we have one material, if I have bar or rod from steel, I apply force until certain amount of the load. The relationship between force and deformation is linear. This region, our formulation for strength of material, it is valid because it obeys Hooke's law. Hooke's law is valid in linear elastic region. Above this point, which they call it limit of proportionality or elastic limit, the behavior becomes nonlinear and we will have permanent deformation. Above that, we need another course, we call it plasticity. But below that, our formulation is right. Now, we know what is the Hooke's law and how Hooke formulate that for spring. Let's come back to this. Again, we have spring, we apply force, we have deformation delta. We know force is equal K delta force is equal stiffness of spring times deformation. Instead of spring, if we have one bar built using steel, material is steel, I apply force F, the initial length is L0, the initial cross-sectional area is A0. First, force is 0, then step by step I increase the force to the F1 value, F2, F3 and so on. So, what is the stress? Normal stress is force divided by initial cross-sectional area. Strain is equal to deformation divided by initial length. So here, if I show stress and strain, assume in first point our force is 0, so stress is 0. If force is 0, deformation is 0, strain is 0 too. Then I increase force to the F1 value. Stress will be sigma 1 because F1 divided by A0, and epsilon will be epsilon 1 because it will be delta 1 divided by L0. Increase to the F2, sigma 2, epsilon 2 and so on. Again, if we have one coordinate, x-axis I show with epsilon strain, y-axis I show with stress, and I show these different points and I attach together. We will have again one line. Here, tangent of this angle will be sigma over epsilon. It will be sigma over epsilon, which we will show with E. And we call it Young modulus. Why we call it Young modulus? Because of Thomas Young. He find this relationship in 19th century. He was physician and physicist. He was British physician and physicist, and he was very genius guy. It is good you read his life story, but because of him, this constant number here, we call it Young modulus. So sigma over epsilon is equal to the E. From here, I can write sigma is equal to E times epsilon. So sigma is normal stress, epsilon is strain, and E is Young modulus. Different material, they have different Young modulus, and it is easy to figure out that number. For any kind of material, for steel, for brass, for copper, for concrete, glass, diamond, we have different number for Young modulus. And how we can find that number? It is easy test. We can conduct easy test and figure out that number. There are tables. They develop those tables in different unit, in SI unit, British unit. You will look at the material name. It will give you the Young modulus. But if you take sample of that any kind of material, if you take one sample and build a specimen using simple stress strain test, you can end up with this curve. So tangent alpha for this line will be E Young modulus. Later on I will explain that test, and I will tell you in that stress strain curve what is the name for each point. Later on we will talk about that. Don't worry about that for now. But for different material, we know the E. E is known value, and if even we have new material, we don't know E for that, it is easy to find E using one simple stress strain test. So, up to now, we know Hooke's line spring is F is equal K times delta. Hooke's law in material, it is sigma is equal to E times epsilon. Instead of force, here we have normal stress. Instead of stiffness of spring, we have Young modulus. and instead of delta we have strain. So here the unit for sigma, for example, it is Pascal. The unit for Young modulus, assume we don't know that, but we know there is no unit for sigma. So what is the unit for Young modulus? Young modulus is equal to sigma over epsilon, because epsilon is unitless, sigma unit is Pascal, Young modulus unit will be again Pascal or PSI, and so on. Usually they report stress and Young modulus in different units. It is good, you know, sometimes they call it kilopascal. 1 kilopascal, it is 1000 Pascal. Or sometimes they report as a megapascal. 1 megapascal is equal 1 million Pascal. Or sometimes they report in the gigapascal. Gigapascal, 1 gigapascal is equal to 1 billion Pascal. So now we know what is the kilopascal, megapascal, and gigapascal. Let's formulate very important formula now in the strength of material, and in order to prove that formula we need only Hooke's law in material. Hooke's law in material for linear elastic material. For linear elastic material, Hooke's law says stress is equal Young modulus times strain. What was the stress? If we come back to initial example, assume we have one bar and we apply external force is F, force divided by initial cross-sectional area A0, we call it stress, is equal Young modulus times epsilon is strain, which is equal to, this is L0, cross-sectional area A0, and the formation is delta is equal delta over L. From here we can write delta is equal to F L over E A0. Or I can write this form as a F divided by E A0 over L0. Both are the same formula. This is very important formula for any bar, rod, anything. Truss member, for example. If we know the internal force, if we know the axial force, it is the force here, for example, we are applying, or in the truss member, axial force, it is internal force in that truss member. If we know that, which we can find that, so axial force times the length of that bar or rod divided by E Young modulus times cross-sectional area. Young modulus for different material is known value. For example, still we know E. Cross-sectional area, for example, here the cross-sectional area, assume it is a square shape. It is 2 inch by 2 inch. I can measure it, so I know A0. So the length I can measure it, for example 3 feet, I know the length. I apply force 200 pounds. What is the deformation? 200 times the initial length divided by Young modulus times cross-sectional area, I will have deformation. Here, if I show in this form, E A0 over L, we call it axial stiffness. K stands for axial, K stands for stiffness, A stands for axial stiffness. We call it axial stiffness. Later later on I will define you different type of stiffness. For example, we have torsional stiffness and so on. For now, if we have axial force and we look at to the axial deformation, we will need axial stiffness. Axial stiffness is equal to Young modulus times cross-sectional area divided by length. So let's review everything one more time. Up to now, we know for any axial member, for example here, one rod we attach to the wall, the initial length is L0, the initial length is L0, the initial cross-sectional area is A0, we apply force F. Normal stress is equal to force divided by cross-sectional area. So normal force is perpendicular. Normal force means we should cut this perpendicular to the bar, and free body diagram. Here we will have external force F and the component of the normal stress. They are perpendicular to this surface. We show with lowercase sigma, we call it normal stress. Deformation for this, under the effect of this force, if it is delta, strain is equal to deformation divided by initial length. We call it strain. If our material obeys Hooke's law, it means they are linear elastic material. Linear means the relationship between force and deformation. They are proportional, and elastic means once we remove the external load, it will come back to the original shape. So for linear elastic material, until certain amount of the stress, which we call it elastic limit or limit of proportionality, the relationship is linear elastic. In this region, Hooke's law is valid and sigma is equal to E times epsilon. Here, tangent alpha, this angle is alpha, tangent alpha is equal to Young modulus, and they call it this E, Young's modulus, or modulus of elasticity. The reason they call it Young modulus because Thomas Young in 19th century, he find this relationship in the material. Of course, it is not something new. Exactly, it is Hooke's law for spring, but he applied that to the material. Thomas Young, he was British scientist. So, in that case, sigma is equal to E epsilon. From here, if we put instead of sigma F over A naught and epsilon delta over L naught, I can write F over A naught is equal to E delta over L naught. From here, deformation delta is equal to external force times the initial length divided by Young modulus times cross-sectional area perpendicular to this bar. I can write this as a F divided by E A naught over L naught. This term I can show with K and this A.